Usually, when you track a massive, like, paradigm-shifting technological breakthrough, the expectation is that the physical footprint will match the intellectual impact.
Oh, absolutely. We kind of expect a massive building, right?
Right. You hear about a new leap in artificial intelligence, and the mind immediately conjures up these sprawling architectural marvels.
Yeah, hyperscale data centers.
Exactly. You picture hyperscale data centers stretching out into the horizon, these cavernous warehouses just vibrating with the hum of 10,000
And
surfers.
then drawing down enough megawatts to power a mid-sized city.
Yeah. You imagine miles and miles of thick fiber optic cable snaking under raised floors, and the lead systems engineer pointing to this monolithic structure and saying, "Oh, there it is. That's the engine."
It's a very human bias. Honestly, we are just hardwired to associate immense capability with immense physical scale.
No way.
If a system handles an unfathomable degree of complexity, we naturally assume the blueprint required to run it must be equally massive.
It's like thousands of pages of documentation.
Right, or millions of lines of C++ code, vast sprawling repositories, the works.
But then you step into the world of theoretical computer science,
Mm-hmm.
and specifically the intersection of discrete mathematics and modern distributed computing, and that sense of scale completely inverts.
It goes entirely the other direction.
It really does. So today, we were looking at an architectural landscape that is almost microscopic.
Which is just wild to think about.
Welcome to another deep dive. Today's mission for you, our listener, is to explore how an incredibly, almost unbelievably tiny piece of code can serve as the fundamental backbone for wildly complex artificial intelligence operations.
We have exactly one file to examine today, right?
Exactly one file. It's titled dynamicpermutation.lean. It was generated on May 1st, 2026, and the file size is exactly 657 bytes.
Yeah, 657 bytes. To put that in perspective for you, that is a fraction of the size of a standard corporate email signature. It is literally a paragraph of text. Yet the operational footprint of this specific mathematical proof is staggering. What's fascinating here is how much power is packed into such a tiny space.
And the words we're going to be throwing around today, things like combinatorial structures, graphs, permutations, discrete mathematics.
They sound intensely academic.
They do. They sound like a graduate-level seminar that you want to sleep through. But this specific 657-byte file holds the absolute key to making chaotic, distributed computer systems work together flawlessly.
And that lean extension on the file, that's the first major clue to what we're actually dealing with here.
Yeah, let's unpack that, because we aren't looking at a standard Python script or, some Rust utility function.
No, lean is a theorem prover.
Okay, so what does that actually mean in practice?
Well, it's a purely functional programming language, and it's used to mathematically verify that code does exactly what it claims to do, with zero room for edge case errors.
Zero room.
Right. It implies a mathematical certainty. When you write something in lean, you aren't just writing instructions for a machine to execute.
Like, do this, then do that.
Exactly. You are writing a formal proof that a compiler verifies. You are basically establishing a foundational law of physics for that specific software environment.
Okay, so your mission today, as you listen to this, is to understand how this tiny mathematical law, this shuffling and unshuffling concept, is the secret ingredient to organizing chaos in cutting-edge tech.
Because the text we're analyzing explicitly states that this tiny file is the, quote, formal backbone for Angle 5B's topology agnostic head TP.
Which is a very dense, deeply technical phrase.
Yeah, mouthful, yeah.
But the beauty of this document is that it systematically builds the logic required to understand exactly what that means, starting right in the internal comments.
Right. It lays out the core mathematical rule right from the jump.
Okay, let's unpack this. The very first line of the comments in dynamic permutation.lean reads, runtime head routing as an equiv on fin n.
And then it elaborates right after that.
Yeah, it says, any routing that permutes candidate indices before attention is a bijective self-map.
That is the cornerstone of the whole thing.
So break that down for us. What is a bijective self-map based strictly on what the text is telling us?
Let's look at the phrase bijective self-map, which the text represents with the Greek letter sigma, or, sigma dollar.
Okay.
In combinatorics, a map is simply a function that takes elements from one set and associates them with elements in another set.
Like drawing lines between two columns of numbers.
Exactly. But the constraints here are incredibly tight because it's bijective.
Meaning it's a strict one-to-one correspondence.
Precisely. Every single input has exactly one unique output and vice versa. There are no collisions, no two inputs routing to the same output.
And absolutely nothing gets left behind.
Right. If you are routing data packets, a bijective map guarantees that no packet is duplicated and no packet is dropped. It is a perfect sealed system.
And then it's a self-map.
Yeah, meaning the domain and the codomain are identical.
Okay, so you aren't mapping a set of data to a new, different set of memory addresses.
No, you are mapping the set back onto itself. You are taking the existing elements and purely reordering them within their original boundaries.
So it's a permutation.
Exactly, a highly controlled shuffle.
Okay, so the document then makes its most critical assertion. It states, quote, applying sigma, then sigma 1 is identity.
Right, so sigma is our permutation, our scramble.
And sigma 1 is the inverse function.
The exact mathematical undoing of the scramble.
So identity, in this context, in discrete mathematics, means returning the system to its precise original state.
A perfect one-to-one restoration.
Let me try to put an analogy on this so we can really picture it. Imagine a librarian.
Okay, librarian.
Yeah, this librarian takes a perfectly ordered row of books, and they scramble them up based on a very specific secret code.
That's our sigma.
Right, that's sigma. So they hand this scrambled row of books to you, and then later they use the reverse of that exact code, the sigma 1, to put them instantly back into perfect order.
Which is the identity.
Exactly. But wait, I have to push back on this premise based on what the text says.
Go for it.
If the end goal is identity, getting exactly back to where we started, why go through the trouble of scrambling, permuting the candidate indices in the first place?
Seems like extra work.
It totally seems like extra work. Isn't that just a massive waste of time? In high-performance computing, any extra operation is a potential latency trap.
That's a really valid point, and it's completely counterintuitive, isn't it?
Yeah. Why introduce chaos when your goal is perfect order?
Well, the text gives us the answer. To understand why we scramble, we have to look at what happens during the scrambled state.
Okay.
And it has everything to do with the rank-based queries. The document explicitly says, so routing composed with its inverse preserves argmax/argmin.
And every other rank-based query. That parenthetical is huge.
It really is. That phrase is the operational linchpin of the entire 657-byte proof.
So let's talk about argmax and argmin for a second.
Yeah, let's break those down.
In discrete mathematics, and specifically in the machine learning attention mechanisms this file eventually references, argmax isn't just looking for the biggest number, right?
No, not at all. If you have an array of values, the max is the actual highest value itself. The argmax is the index.
The specific location or coordinate in the array where that maximum value lives.
Exactly. It is fundamentally a spatial or structural query. It relies entirely on the hierarchy and the relative location of the data.
So what the text is doing here is providing an ironclad mathematical guarantee.
Yes, because the permutation is a pure bijective self-map, it doesn't destroy or alter the underlying values.
It only changes their locations temporarily.
Right. So if a specific data point was the argmax, the most critical piece of information before the scramble, it remains the argmax during the scramble.
Even if its physical memory address is temporarily changed.
Exactly. And when the inverse, the sigma 1 is applied, the hierarchy is perfectly preserved. That argmax snaps right back to its original index.
That is wild. And going back to that parenthetical and every other rank-based query, the implications there are just immense.
It's basically a mathematical blank check.
It means that any operation relying on the order or relative value of the data is totally safe to execute.
You can scramble the indices, blast the data across a massive distributed cluster, perform your rank-based processing, and as long as you hold that inverse key,
you can trust the final result.
With absolute certainty.
Think about how you, the listener, prioritize tasks in your own life. If someone scrambles your to-do list, your most important task, your argmax, is still your most important task, right?
Right. The task itself didn't change just because it moved to the bottom of the paper.
Exactly. And once the list is unscrambled, its priority, its exact position, is perfectly preserved.
That's a great way to visualize it.
But, preserving data is great in theory. We still need to know where this is actually being applied in the real world.
Right, the physical application.
Here's where it gets really interesting. Let's pivot to the specific architecture mentioned in the text. Angle 5B.
Yes, the text says, this is the formal backbone for Angle 5B's topology-agnostic head TP.
Okay, head TP. We can safely assume that refers to tensor parallelism at the attention head level.
If we connect this to the bigger picture, in massive AI models, you can't fit the entire matrix of weights onto a single GPU. It's just physically impossible.
Right. The memory constraints are too tight.
Exactly. So you use tensor parallelism to slice those massive tensors into smaller chunks and distribute them across multiple processors.
And synchronizing those processors is historically a nightmare, isn't it?
Oh, it's the biggest bottleneck in artificial intelligence. Normally, you have extremely rigid communication rings. Every GPU needs to talk to every other GPU in a very specific synchronous order.
Right. It's highly dependent on the topology.
The physical wiring, the switches, the network layout. If the topology is rigid, the compute is rigid.
But the document specifically calls Angle 5B topology agnostics. Let's look at that.
Agnostic, meaning the system simply does not care about its physical or network layout.
The workers can be arranged in any way, and the system still functions.
Right, a mesh, a star network, completely fragmented, it doesn't matter.
The text actually describes the scenario perfectly. It says, the order in which workers return partial head outputs doesn't affect the final aggregate.
Yes.
So let's focus on those workers returning partial head outputs. I like to think of it like a highly uncoordinated restaurant kitchen.
Okay, I'm listening.
You have multiple chefs, those are our workers, and they're cooking different parts of a massive meal, right? Those are the partial head outputs.
Right.
Chef A might finish the dessert long before Chef B finishes the appetizer.
In a traditional setup, that's a disaster.
Exactly, because the meal has to go out in order. But here's the aha moment of the whole system. Because of the mathematical guarantee we just talked about. The argmax preservation, the order of the chef's finishing, doesn't matter.
Because the system doesn't wait sequentially?
Right. It accepts the partial outputs as they come, in whatever chaotic order. It accepts the dessert, it accepts the side dish, because it knows, mathematically knows, that it will apply the inverse repermutation to sort everything out perfectly at the end.
You introduce temporary, controlled chaos at the routing stage, which allows the compute layer to run infinitely faster. You aren't bottlenecking your fastest chefs waiting for your slowest ones.
But wait, what happens if we forget to apply that inverse? Like the text specifically says it must be applied before the output projection. What is the catastrophic failure if we project the output too early?
If we mechanically break down before the output projection, we are talking about the point of no return.
The final step.
Exactly. The output projection is where the data is finalized and sent forward to the next layer of the neural network. If the inverse, that sigma, isn't applied before that happens,
the final aggregate is permanently garbled.
Completely destroyed. You've lost the semantic meaning of the tensor. The inverse acts as the vital gatekeeper before that final step. You have to unshuffle before you project.
It's amazing how this purely mathematical theory solves such a massive logistical bottleneck in distributed computing. But it makes me wonder, what specific machine is actually using this 657-byte backbone today?
Well, the author of the file actually left us a massive clue at the very end of the source text.
Yes. Let's look at the actual code snippet provided at the bottom. It says namespace dynamic permutation.
Right, so let's dissect that terminology first. A namespace encoding is just a way of organizing and encapsulating this specific mathematical function.
So it doesn't bleed into other parts of the system.
Exactly. It isolates the dynamic permutation logic. But the really juicy part is the next line.
Yeah, it reads, abrev dim nat, 32 number of attention heads for Gemma 431b.
Okay, so they define a variable, dim, which stands for dimension.
And it's set to a natural number, nat, of 32.
But the comment is what gives the whole game away.
Number of attention heads for Gemma 431b. That is a huge revelation. This exact piece of code, this tiny lean file, is built specifically for Gemma 431b.
Mapping directly to its attention heads.
So what does this all mean when we put it together?
Well, if we synthesize everything we've talked about, the 32 attention heads of Gemma 431b act as our 32 workers.
The 32 chefs in the kitchen.
Right. And instead of forcing these 32 heads to process information rigidly and sequentially, which would create massive latency, this tiny file allows them to dynamically route.
The runtime head routing from the very first line.
Exactly. It allows them to process independently and return their partial outputs asynchronously.
Because the math, the equiv on fin, guarantees it's safe.
Yes. It ensures that no matter how jumbled the 32 outputs get during the massive processing load, they perfectly, flawlessly snap back into place before the final output.
So if you are listening to this and you appreciate efficiency, you're witnessing something incredible here.
A total paradigm shift in how we handle data flow.
You are seeing how a single, elegant mathematical truth completely eliminates traffic jams inside a highly complex 32-head architecture. It just bypasses the physical limits of the hardware by changing the rules of the road.
And that raises an important question, doesn't it? In an industry absolutely obsessed with scaling up.
Throwing more GPUs at the problem.
Right, adding more hardware, more complexity, more physical wires. Sometimes the most profound optimizations come from just a few lines of foundational mathematics.
It's a testament to the invisible infrastructure that truly powers our world. Which brings us to the end of our journey today. We started way out in the abstract concepts of discrete mathematics and combinatorics.
We looked at bijective self-maps.
Right, and argmax queries and preserving hierarchy. And finally, we arrived at the very real-world application of managing 32 asynchronous attention heads in Gemma 431B, all from 657 bytes of code.
It's mind-blowing when you really step back and look at it.
It really is. And I want to leave you, the listener, with a final provocative thought to mull over.
Oh, I like where this is going.
The text we analyzed today proves that introducing temporary controlled chaos, the permutation, actually allows a system to move faster and more freely.
Provided you have the exact key to restore order at the end.
Exactly. The inverse key is non-negotiable. So think about your own life, your own work. What rigid sequential systems are you clinging to? What processes could genuinely benefit from a little topology-agnostic chaos?
Letting things run asynchronously.
Yeah. Provided you knew exactly how to unshuffle the results before the final output projection. Sometimes trying to control every step of the process is what's actually slowing you down.
A little controlled chaos goes a long way.
It really does. Thanks for joining us on this custom-tailored deep dive into the hidden architecture of discrete mathematics. We'll catch you next time.